Okay, first topic in our matrix series, linear equations. We're going to talk about what a linear equation is, what does linearity really mean more generally, what are some examples of these, and what constitutes a solution to a linear equation. Alright, the simplest linear equation is just ax is equal to b, where x's are unknown. We will come to call these indeterminates or unknowns, or if you like, variables. But ax equals b is our simplest linear equation, and you should know by now how to solve this. You divide both sides by a, assuming a is not 0, and you have x is equal to b over a. And what does this represent? Graphically, this represents a line going through the point on the x-axis whose x-coordinate is b over a. In particular, if we have our x and y axes as shown right here, then this line represents what we call the locus of solutions to this algebraic equation. And this locus consists of all the points whose x, y coordinate pairs satisfy that the x coordinate is equal to b over a. In other words, x is equal to b over a. This is exactly what that says. So this is our simplest example of a linear equation. Now, if we generalize a little bit, if we choose a1, a2, and b, just real numbers, and x and y are our indeterminates, then a1x plus a2y equals b is the standard form of a line in the plane. This is a linear equation which, you guessed it, represents a line, and any line in the plane can be represented by this equation simply by choosing appropriate a1, a2, and b, which are just numbers. Once again, what does it mean for this equation to represent, say, this line? Or what does it mean for this line to be the graph of this equation? Well, it means precisely that for any point xy on this line, that if we plug in this x coordinate, right, which is down here, and this y coordinate, which is over here, if we plug it into this equation, it will be true. It will be a true statement. And if we plug any point, say x prime, y prime, that is not on the line into this equation, it will not give us an equality of both sides. Let's generalize a little bit further. Suppose we have, instead of 2 indeterminates x and y, 3 indeterminates x, y, and z. Suppose we have ax plus by plus cz is equal to d. This, I'm claiming, is also a linear equation, but in 3 unknowns instead of 2. And what does it represent? Well, it represents the higher dimensional analog of a line in 3 dimensions. What is that? A plane. This is the equation of a plane in R3. If A, B, C, D are just numbers, you can write every plane in 3-dimensional space with some A, B, C, and D like this. Now, as we generalize further and further and essentially keep adding more variables or indeterminates, it's going to look very similar to this, although we're going to want to be systematic and not call things A, B, C, and D because we'll run out of letters in general. So we'll use subscripts instead, like A1, A2, and even for our indeterminates, we'll use, for instance, instead of x and y, we will use x1 and x2 to represent our 2 variables. So now, to get completely general, our most general form of a linear equation is going to look like this. A1, a number times a variable, plus a number times a variable, plus a number times a variable, etc., all the way up until, well, whenever we decide to stop, let's call it n. After n of these terms, and then this is going to be equal to some constant. So our a's, we're going to call the coefficients. Our x's, we're going to call our unknowns or indeterminates. And our b all over here by itself, we're going to call this the constant term. And with the exception of our addition signs and our equal sign, this is the complete anatomy of a linear equation. It's very basic. You have indeterminates multiplied by coefficients, added together, and in general that's equal to some constant term. As I told you in the introduction video, I expect you to be familiar with summation notation, which if you want to look up a video on that, it's not too complicated. And if you want to take advantage of that, this can be written much more compactly as the sum from I is equal to 1 to n of a sub I times x sub I is equal to b. This is our general linear equation in n unknowns. Now, what do we really mean by linear? What separates a linear equation from a nonlinear equation? Well, we already said ax plus by is equal to c, or if we want to plug in specific values, let's say, how about x plus 2y is equal to 5? Right? This is a great example of a linear equation. What could I do to this to make it nonlinear? Well, if we were to raise one of the variables to a power other than 1, so x squared plus 2y equals 5, this is now a quadratic equation. It is no longer a linear equation, an equation of order or degree 1. That is what constitutes a linear equation. It's precisely one which is of degree 1 in every variable, right? So what other features distinguish a linear equation from a nonlinear equation? Well, the fundamental property of linearity is basically the following. So if we have a function and we're taking as an input a number, say 3 times a variable, plus another number times another variable, whenever we have this as an input to a function, you can always do this when the operation here, f, is linear. You can always say that this is equal to 3 times f of x plus 6 times f of y. This is the very definition of linearity. You can bring constants outside and you can split up the sum of the operation is the same as the operation of the sum. So it doesn't matter whether you add before taking the operation or after, they're the same. This is the property of linearity. Notably, what functions don't have this property? Well, for instance, x plus y squared does not have this property. This is equal to x squared plus y squared plus 2xy, right? If this 2xy weren't there, then this would be okay, right? Because this sort of distributes to each of them. But it is there, and so this is not a linear operation. Once again, how about the sine function? Sine of x plus y, you should have learned, or actually let's use cosine. Cosine of x plus y is equal to, we know from trigonometry, cosine of x, cosine of y, minus sine of x, sine of y. Notably, this is not equal to cosine of x plus cosine of y. This is what we would expect if this were a linear operation. It is not a linear operation. So, once again, we only want variables of degree 1. Now, you can have whatever numbers you want out front of those variables. For instance, in our equation of a line, let's say cosine of 40 degrees times x plus sine of 20 degrees times y is equal to tangent of 10 degrees. This is completely fine because when you take this cosine operation of a number, this is just another number. Our indeterminates are not just numbers, right? They're indeterminates. They have special status. They're variables. So we can have whatever numbers we want with whatever operations we want on them out front, but the variables themselves appear only to degree 1. They're not multiplied by each other. That's another thing. We will not see xy is equal to 1 or y equals 1 over x. We will only see some number times x plus some number times y equals another number. This is what it means to have a linear equation. Okay, so what constitutes a solution to our linear equation? Well, just like any other algebraic equation, in n variables, n unknowns, we want an ordered n tuple, which is like an ordered pair, right? We have ordered pairs, but we can do more than just two. We could have an ordered triple, we can have an ordered quadruple, or we could have an ordered n tuple. And a legitimate solution to this linear equation just consists of an ordered n tuple such that if we set xi equal to yi for every I, this symbol means for every. If we set each of these, so if x1 is equal to y1, x2 is equal to y2, all the way up to xn is equal to yn, then it satisfies this equation. That is what constitutes a solution to a linear equation. More generally, a solution set is the set of all such n tuples which satisfy a linear equation, because there could be one. In fact, there could be a unique solution to a linear equation, as in the case of ax equals b, there's only one number x which satisfies this, namely b over a. Or, in the case of when you introduce more unknowns, you could have, in fact, infinitely many solutions to a linear equation. So a solution set is going to be some way of characterizing all the solutions, all n tuples, which satisfy this equation. Here's an example where we have infinitely many solutions and what we do in that case. So if we just add 3x2 to both sides, we get x1 is equal to 3x sub 2 plus 6. And already you see, choose any number you would like for x2, and then that will uniquely determine the right side and thus the left side also, so that x1 could be considered as a function of x2 here. Pick any number, again, any real number x2, and there is a real number x1 such that the two satisfy this linear equation. Equivalently, x2 could be considered a function of x1. Pick any number on this side, and there is a unique number which we could solve for on this side, which makes this statement true. And in this sense, I'm going to call x2, or equivalently x1 here, but just one of them, I'm going to call a free variable in this sense. It's free because it can take on any value it wants to, and then this variable is going to be dependent on the free variable. A second way of characterizing this solution set would be to say, let's call x2 equal to t, where t we're going to call a parameter. T is just a new variable we're introducing. And we know x2 in terms of t. Can we also determine x1 in terms of t, so that we have a solution set in both in terms of x1 and x2, or the coordinate pairs, in terms of t? Well, yes, we can. We know that x1 is equal to 3 times x2, which is just t, plus 6. So now we have a solution set. In fact, we can write it as coordinate pairs as 3t plus 6t. And for every value of t, this will give you a coordinate pair which satisfies our linear equation. In fact, this is a parametric form, if you will, of the line that this equation represents in the plane. Finally, we're going to do another example with the parametric form of the solution set, because this is a topic which is going to recur again and again. So we have 2x1 plus x2 minus 5x3 is equal to 0. This is our linear equation in 3 unknowns. So what I'm going to do here is I'm going to set x1 equal to a parameter s, which is notably free. It can take on any value it wants. And then I'm going to set x3 equal to another parameter, t, Once again, it's free. It can take on any number. So now what are we left with? Well, we're left with 2s plus x2 minus 5t is equal to 0. And if we move these two terms to the other side, this gives us x2 is equal to 5t minus 2s. Now if we line all these up together, we have x1 is equal to s, x2 is equal to 5t minus 2s, and x3 is equal to t, which again we could write as a coordinate triple this time as s, comma, 5t minus 2s, comma, t. This is the parametric form of our solution set, and for different values of s and t, it's going to trace out an entire plane in three-dimensional space, in x1, x2, x3 space, as opposed to x, y, z. So this coordinate triple with s and t ranging over all real numbers represents the parametric form of our plane.